Okay, so we talked about relational schemas and how we can implement that using SQL and build tables and then fields that refer to each other in relationships. So that's the lowest level of abstraction that we're going to go and to implement our databases, right? But alongside with that, we have to consider other ways to think about data representation, right, in a little more abstract sense. And so one of the more common ways to do data design is not to actually consider the tables and fields and whatnot. Instead, is to consider them in some more high level of abstractions using perhaps diagrams, right, where something we could draw and we can point at and refer to it and make it much easier to talk about it and describe it. The more common way is to use the unified modeling language, class diagrams. It's a common language that most software engineers will be familiar with, that regardless on what particular language you might be familiar with, it's something we can all point at and have a discussion about data in general. So let's talk about data design, and we'll see some challenges that we might run into when we are designing databases. Right? In particular, any biases, any preconceived information we might have about a particular domain that could be beneficial or not beneficial. Right? So certainly, knowledge on a particular domain should help you, right, understanding the concepts that are being related to one another, but it should not blind you to whatever the specifications or for a particular project might be telling you of how to organize the data. So the requirement should always be the guiding principle on what the data structure, the structure of the data should be. Right? We'll see how reading certain requirements one way or another could make a big difference on how you would structure it. So let's try to consider first a very trivial example where you might have a whole bunch of set of CDs, a library of CDs that you might have been collecting over the years, and now you know databases, and you just learned it, and you want to create a database to capture all the information about your big collection of CDs, right? And you knowing music and knowing CDs, you might come to a first approximation of what that data structure might be. It says, well, certainly you might want to capture the CDs as entities, right? As a physical object plus some electronic representation of that object. And then you might also say, well, a CD might contain a whole bunch of songs inside, right? So you might represent that perhaps as different tracks instead of those CDs. And from your understanding of having listened to lots and lots of music, you might come up with this initial schema, right? This CD as a table, perhaps a unique identifier. You couldn't think of anything to make it unique. The title of the CD, when the CD was released, the band in that CD, the genre, and for the track, you might have a unique identifier for each track, what CD it belongs to, right? It's a foreign key that references the CD, the track number 1, 2, 3, and so forth, the title of the song, and how long that song is. Okay, and for you, it's a no-brainer, right? And you go through your first dozen of CDs, and they all nicely match all this information as you're filling it out, all your data entry. You come to the 13th unlucky CD, and somehow it doesn't fit. Right? It's a CD that you burned yourself that has from multiple bands, from multiple genres. There is no real release date. It doesn't fit perfectly into our schema. And so you might find, well, this is an outlier, right? It's a CD that I made myself. Obviously, it's not going to fit into my schema, right? So I'll just put it to a side. It doesn't fit into my schema. So you you go through a couple of dozen other CDs, and they all fit nicely in your schema. But you come up to now another CD that you did purchase, which is a best of CD that captures lots of songs with from a particular genre, but from multiple bands, right, playing the same genre. So now you say, well, how do I deal with this, right? Certainly, my schema doesn't fit because it has multiple genres, right? And then you come for another one, it has multiple bands for the same genre. And so you might be tempted to, for instance, says, well, I'll change my understanding what genre is. Maybe I'll make it plural, right? That might have multiple genres, yes. And maybe instead of this being a particular genre, it could be a comma-separated value of genres, right? And now you've broken the first rule of normalization, right? First order normalization. You've broken that particular rule. We'll talk about that a little later. But you see how challenging is on something so trivial that your particular misunderstanding on how the structure of the actual data is doesn't fit you with a particular schema, right? And this is a challenge. It's not trivial. It's not a trivial task to come up with a structure that actually represents the entire data set, right? With all its edge cases, with all its special cases, right? That are telling you that perhaps you need more tables, right? To structure it in a particular way. So if you find a whole bunch of genres that might be for a particular CD, maybe this shouldn't be just one genre. Maybe this should be its own table, right? Called genres that has an enumerated list of all the possible genres, right? And then you can then create a mapping table that says, hey, these are all the genres for that particular CD, right? Or for that particular, or maybe the genre shouldn't be part of the CD. Maybe it should be part of the track, right? Where a particular track is a particular genre, and you can have multiple things like that. So this going back and forth of determining whether something is an attribute or it should be its own table, okay? Or it should be moved from one table to another table, right? It's non-trivial, okay? And your first assignment will be making those kinds of decisions, right? You'll be given a specification, you'll be giving a narration of a problem, right? And you'll be making these decisions, right? Should it live here? Should it live there? Is it an attribute? Is it a class? What is it? Okay. So anyway, so the shortcomings of this particular schema, we can list them here. That these are some of the things that this particular schema doesn't allow us to capture. What if there's multiple genres, multiple bands, something that you burn yourself, right? It doesn't match your particular schema. So sometimes it's useful not to think about these problems or the structure of the data, not to think about tables at all, or tables or fields or anything like that. Instead, oftentimes it's better to think about it in a more higher level, in a more conceptual level. And we'll introduce that as one of the more common ways to think about it is to instead use class diagrams, right? A visual representation of that same structure, but with diagrams, with pictures, right? That we are very visual, and we think better in an abstract sense. So class diagrams allows us to capture each one of these concepts as boxes. So each one of these concepts will be represented by some rectangular visual representation. So and then all the attributes, all the fields that describe that concept will be captured as attributes or properties of the classes. Okay. So one of the things that we'd like to be able to do is identify how is it that we can maybe map these two worlds, right? The relational world where there are tables and fields and foreign keys and primary keys, map them to a graphical representation that might look like this, right? So for instance, in the previous set of slides, we looked at tables that represented students and sections and departments and enrollments and whatnot. Well, here's an equivalent class diagram. Okay? We see that we have the same names, right? Enroll, section, course, student, department. But we also might have here also properties. The kind of the same properties that we capture in the fields in the database, right? In the relational schema. One of the things that you'll see that is missing from here is that we don't have any primary keys and we don't have any foreign keys. You see that? And that's on purpose. Right? So instead of, because what were they? What were these primary keys and foreign keys? Really, they did not really describe the concepts. right? Social security number does not describe me, right? Other than the taxes I have to pay. So just like that, any primary key is not really part of the natural description of what the concept is, right? It's only a mechanism to guarantee uniqueness. It's a mechanism for the database to enforce certain constraints, but it's not really part of the data. Yes? So here we only have the fields that describe that concept, right? Course has a title, department has names, students has first name, last name, the date they graduate, and whatnot. Instead of primary keys and foreign keys, what we have is these lines. So these lines establish a relationship between these two classes. It says that somehow the section is related to an enrollment, that a section is related to a course, that courses and departments are related to one another. Okay? These are also referred to as associations, right? A course is associated to section, right? And these numbers on each side of the lines specify how many of each are participating in that association. Saying that one course is associated to multiple sections. So star meaning many of these. So one of those is associated to many of those. Same thing here. A department is associated to multiple courses. One department is associated to multiple students. Here we have something of a misnomer here. This is a little bit different. An enrollment here has multiple one-to-many relationships, right? And what really this is doing is that it's establishing a relationship between two. The student in a section is saying that many students are associated to many sections, and many sections are associated to many students. Okay, we could have captured that by just having a line between these two and saying star associated with many stars. Many sections to many students. Yes? Right, that would be fine, except that this association here would not describe additional information, additional meta information, such as maybe the grade you got, when you were enrolled in that section. Right? The line doesn't capture that. There's no way to, all these lines don't have any fields, right? There's no field that I can store any information about it. Yes, right. So instead, what we did is instead create a separate table that creates a relationship, right? But it describes the relationship, right? There's a piece of field that I can actually provide information about that association. These tables are typically referred to as an association class. It's a class that describes the association between two other classes. Okay, it's sometimes is captured in a different syntax where you have a line going between these two, and then you have a dotted line right to the association class. You'll typically see it both ways. Okay. Sometimes it's also referred to as a mapping table, right, which is mapping references or instances of one class to instances of another class. Right? These numbers here are referred to as cardinality. How many are participating on each side of the association, and it has a syntax. The generic syntax is that it has a minimum and a maximum, right? And of which we have examples here. We might have at most one is participating. So you have some shorthands here where asterisk is actually a shorthand from 0 to many, a minimum of 0 and a maximum of many. And 1 is just a shorthand from a minimum of 1 and a maximum of 1, right? But this could be anything. N could be 2 and 4. Right? So for instance, I might say here that teams here might be of between 2 and 3 students, or 2 and 4 students. So it'd be 2.4. So these would be annotations. Now some of these relationships, some of these are so common that you have a 1 on one side and a many on the other side. Some of these are so common in class diagrams that they have their own names. Right? We refer to a one to many. We call it a one to many relationship or many to one. Right? So it's a very common nomenclature of saying that two classes have a one to many or many to one relationship. Here's another one, very very common, where you might have one student associated to one particular permit, right? One student wants to park in the university. Well, they'll be given one permit per car that they bring. Or maybe you might have a track associated to a particular lyric. One song only has one lyric, right? You might have multiple single association. Or you might have a many-to-many, where one student might be enrolled in two departments, right? Maybe a major and a minor, right? They're graduating in two different departments. So here's a many-to-many, which is perfectly fine. Now, typically, in UML, it's perfectly fine to capture this relationship this way, star to star. But if you're going to convert this into a relational database, there's no way in relational database to actually implement this, right? Where you might have multiple foreign keys, right, on one record, right, referencing to multiple primary keys on the other. Right? There's no way to actually implement this. So typically, we convert this, so that we can actually implement it in a low-level representation as a relational database. We will replace this many-to-many drawn like this. We'll replace it with putting another class in between, right? That will do the mapping. It'll say that some of those are related to a whole bunch of those, right? Meaning we can replace it with a table that has two foreign keys. That has a record with two foreign keys. That's exactly what the enrollment table does, right? It has two foreign keys pointing to a student, pointing to a section. When we replace a many-to-many like this by something that can actually be concretely implemented, we often refer to that as saying that we are reifying. We are converting it to something that can actually be implemented. Okay? So at this conceptual level, it's just fine to keep it like that. But when you're going to implement it, you'll need to reify and convert it to something that is more concrete. Now, these names, oftentimes, these have a nomenclature or a naming convention that if you know exactly how many are participating, if you know exactly that there's exactly 2 or 3 or 4 instances that are participating in the association, we say that's a strong commitment. Those 3 are committed to participating in the relationship. If you're on the side, you don't know how many are participating, maybe 0, maybe 1, maybe many. We don't know how many. We say that it's a weak relationship, right? We don't know how many. Maybe nobody. Maybe there are nobodies on the other side, right? We say it's weak, right? So we often say that this is a strong relationship. You might have 2 students, 3 permits. It's a strong relationship. Or it's a strong, weak relationship, or maybe a weak. This is a weak-to-weak relationship. Maybe there are no students. Maybe there are no departments. Nobody's enrolled anywhere. There's no university. So we call that the relationship strength. So many-to-many is a strong, is a weak. A one-to-one is a strong. And here's just some examples of a weak, strong, weak, or strong relationships. Now, just by inspecting the class diagram, we can immediately, very quickly see, visually, how we can navigate from one class to the other class, right? By following the relationships, following the associations. We can quickly be able to answer certain questions that you can, if you're given the students, you can identify where they enrolled, which courses they enrolled. If you know the courses, you also see who's enrolled in those courses. If you give me a particular student, you see who taught him for a particular section, right? Just by perusing and looking at the diagram visually. So it's very useful to have a graphical representation. Oftentimes, we use some powerful tools that can reverse engineer a relational database, right? We can point it to a database. It can parse all the create statements and whatnot. Right, parse the schema and provide to us a nice graphical representation of the database, right, which allows us to very quickly be able to answer certain questions. Oftentimes, these tools allow us to do reverse engineer it and also regenerate the schema. It can generate graphically. We can modify the schema, push a button, and it can then update the schema accordingly. Pretty cool. It can also be applied to other data models, like maybe pointed to a Java data model, or C# or some object-oriented data model, and then it can create, again, a UML representation of that particular data model. Or it can do both ways. It can go from Java, you create a graphical representation, you press another button, and it can create the schema for you. So you can do the mapping between these two worlds, right? Between an object world and a relational world, which is pretty cool. And it can generate any language and any representation you want, XML, and any representation, any data representation. Anyway, so we would like to identify a way where we can systematically be able to convert from one world to the other, right? From this graphical representation to a relational schema, or vice versa, from a relational schema back to this world. And it's not always trivial. Okay, it's not always immediately obvious. So let's focus on these cardinalities and see how they would be implemented in an equivalent relational database. So in an equivalent relational database, it might look like this. Right? You have these tables where you might have one course over here being referenced by multiple sections. Here you have many sections, right, referencing one particular course, and here are some other sections referring to another course here. And whereas over here you have many courses being taught by the same department. You have foreign keys referencing a single department over there. So we see that these cardinalities, these associations, have a one-to-one meaning or mapping to foreign keys and primary keys, something related there, right? Where we have these foreign keys referencing to that particular primary key, these foreign keys referencing that particular primary key, and so on and so forth. So somehow they're related to one another, right? These cardinalities and these associations, right? So one of the things that we can by looking at these diagrams, not only the things that we know we can determine, there are certain things that we know that we cannot determine, that is not being captured in the database. For instance, nowhere in the database are we capturing the fact, if a student changed majors, that's not captured anywhere, right? The history of whether you were in a particular department and you changed to a different department, or maybe you enroll and you withdrew from a course, that's not captured anywhere. None of that history is captured. So we immediately see that that's information just not there. We cannot answer any questions about that, or where some professor is advising a particular student. So anyway, we would like to be able to identify a way that we can go back and forth between a class diagram and an equivalent relational table. Some of these are trivial. For instance, we already can see that classes and tables are kind of like a one-to-one mapping between them, right? Or we can see that attributes and fields also looks like it's a one-to-one mapping. We can see that relationship, those lines and those cardinalities in the class diagram have a mapping directly to foreign keys and primary keys. So from that, we can deduce somewhat of an algorithm on how we would go about implementing that, right? So for instance, let's consider first this trivial example, the one we had earlier, right? That we have the CDs, we have the track. We're going to go we're going to complicate things just a little bit further. We're going to add an additional table called the lyrics table. So this lyrics table, notice that has. So notice that this is it's bold and it's underlined, so it must be a primary key. Yes, but it's also bold and italic. All right, so that means that this is also a foreign key. So that's new, right? So here's a field where it's both primary key and a foreign key. Okay, that means that and notice that we to make it simpler, we gave it the name of the primary key that it's referencing. Right, so here's a primary key, track ID, and we have here a foreign key that is referencing its track. It's saying that there's a lyric, the words to a song references a particular track. Right, so if you want to look at the words for a particular song, look it up in some other table. Okay, so what this entails of having a primary key and a foreign key, this is both telling me that I exist only because that track ID exists. Right? If it doesn't exist, I could not exist. Okay? It's also unique, meaning there's only one of me here, right? So that means there's only one for one of those. So this is one way that you can enforce, for instance, a one-to-one relationship, right? There's a one-to-one relationship between a particular song, a particular track and its unique lyric, as opposed to the CID where it's only a foreign key, right, that is referencing a primary key. That establishes a one-to-many relationship, right? One CD having many tracks, right? So this here, where you have a primary key that is also a foreign key, it's a way of implementing a one-to-one relationship. Yes? Okay. So anyway, having introduced that small complication, we can come up with some algorithm that would allow us to create to convert between these two different walls. Here's some examples on what would it look like. Right, here's a couple of CDs and tracks that reference that CD, and here's some foreign keys and primary keys for the lyrics that uniquely match to an equivalent track. So all right, so here we have we know that these foreign keys and primary keys map nicely to the one-to-many relationship, right? The primary key of one CD referenced by multiple foreign keys in a track, so one-to-many. So the algorithm might look something like this, right? The generic algorithm. So first, the few things are very simple. Create one class for every table. So we knew that already, right? The other one is we're going to look at the relationships, right? We're going to look at the associations in the class diagram. We're going to look at the foreign keys and primary keys in a schema, and wherever we have a foreign key and primary key, we're going to have an association between the classes. Yes, but we need to look at the primary keys and foreign keys. If it's just a foreign key, then we know it's going to be on the weak side, right, of the relationship. Right? If you have the primary key, you're going to be on the strong side of the relationship. Yes, right. And so this is what this establishes. But in addition, if that foreign key is also a primary key, right? If that foreign key is also a primary key, that means that you are also it's going to be a one-to-one relationship. So this is what these rules capture. It also adds a couple of rules on whether you were using your keys were natural keys or artificial keys, right? If you don't have a primary key that is natural, like maybe a username, right? Or maybe not a username, but maybe an email, right? That it's a natural representation of somebody, then just make one up, okay? Make up an artificial key. So for instance, if we apply the algorithm to this schema, ideally you would come up with the original class diagram that we were showing you, right? So for instance, we have 5 tables, we have 5 classes. We have student and departments. We have the primary keys, and we have the foreign key and the student referencing the department. So that's going to create a one-to-many relationship to that class diagram, which is represented between the student and the department, a one-to-many relationship there. Anyway, if you run the algorithm, this is what you would come up with. Okay. Right. So why would you do this, right? And we mentioned earlier, right? It's so much easier to parse a visual diagram than to parse text that describes some tables. And very commonly would be that if you want to make any modification to a schema, a relational schema, you would first create the UML class diagram that equivalent to that schema. Then you could make some design decisions, architectural decisions, any changes you might want to make, and then you would reconvert it back into the equivalent schema. It's easy to understand, easy to create queries. You can go the other way around. You can instead start from the class diagram and create the relational schema. Again, for every table, you would create a table for every one of the classes. If you have a primary key, that's going to if you have an asterisk, that's going to be a foreign key. If it's going to be a primary key, that's going to be on the strong side. And depending on whether it's a one-to-one or one-to-many, you create a weak-strong or strong-weak relationship between the two. Okay, so meaning if you start from this class diagram, ideally you would come to the conclusion that this is the equivalent relational, right? and you can certainly run through that algorithm and validate that indeed you create these two mappings between these two worlds. Okay, a couple of things that our algorithm cannot handle. Right, one of the things that it cannot handle is if you have a many-to-many. Like for instance, if you have a many-to-many between students and sections, our algorithm you can't deal with that. Right, so we'll extend our algorithm a little later to deal with these edge cases. Right, to like a weak relationship, it cannot handle. Anyway, so here's the resultant schema. You would additionally try to simplify your schema, right? Looking for any optimizations that you might make. For instance, you might determine that the title of the courses are unique enough that it could serve as a natural key, that the department name is also unique enough that it could be a natural key. Okay. For instance, there might be a rule in your specifications that a student cannot be enrolled in the same section more than once. Yes. So that might be captured by choosing the combination of student ID and section ID as a combined key, right? So kind of removing the necessity for this artificial key, right? So you could have a primary key that is a combination of these two instead, right? So those kinds of decisions, you would try to simplify the schema as much as possible. Okay, so let's go through that real quickly. For instance, you might decide that the department name is unique enough and just remove the DID, right, and make the department name the primary key instead. If you make that change, you need to go back to the other tables, right, because there's a whole bunch of tables that are referring to this table, right? The students is referring to it, the course is referring to it, right? So you need to change them as well. So you need to go back to the student and change, instead of the major ID, change the major name, the name of the department, right? And same thing for the course. The permit, you might have decided that there's really no need, since one student gets one permit, right? You can capture that and remove the artificial permit ID, and instead use the student ID, which was just a foreign key before, referring to the student, and making it the primary key and a foreign key. Right, so that implements the one-to-one, right? And I'm referring to that one student, and so it's a foreign key and it's a primary key, meaning it's unique, right? So we can replace the permit ID. What else can we do? Yeah, so this also, there might be a rule that enforces the fact that students cannot enroll more than once in a section. So you could use that as a primary key, the combination of those two, and remove this artificial key. What else? The course. Right, we had changed the department name as a primary key of the department table, so we're going to replace the department ID with the department name. Also, we've agreed that the title is unique within the university. Courses are not allowed to have the same names, right? So that's enough to be a primary key. What else could we do here? The section used to refer to the course, but now it can refer to the title of the course instead. Right? So now it's easier to follow and understand. Yeah, some limitations, right? It doesn't handle strong. It doesn't handle inheritance. It doesn't handle a whole bunch of other things that class diagrams allow you to do, right? That our algorithm doesn't handle. But we'll talk about it a little later. So anyway, since the fact that it's better to work at a higher level, represented perhaps in a class diagram in a visual sense, it makes sense to always work first in class diagrams before you commit to any particular data representation, whether the data representation is SQL or XML or object-oriented representation. It's always better to start at a class diagram. So a lot of effort would go into getting the class diagram right. That's our first step: get the class diagram right. First of all, it's create the requirements. Look at the specifications, right? That's the hardest part, the requirements. Right? The requirements is the result of having had multiple meetings with your client and having oftentimes frustrating meetings that they're contradicting themselves. One day they tell you one thing, the other day they tell you the opposite. And depending on who you ask, they'll tell you something different. And sometimes things are vague or ill-defined. They'll use the same different nouns to refer to the same exact thing. So it's our responsibility to vet these things, right? So yeah, so the requirements is the most vulnerable part of a project. But assuming that you have a requirement, or you have a rolling requirement in an agile sense where you learn it as you go, and you gather those requirements when it's most appropriate. Those requirements eventually need to be converted into something formal, some formal representation. So you'll first create some preliminary class diagram, perhaps a very naive first attempt at a class diagram, and perhaps you're bound to make mistakes and assumptions, but that's fine. You'll first come up with a first approximation. You'll gather all the nouns, all the verbs that are going to give you clues of what things are classes, what things are fields. Typically, nouns will give you a clue on what classes you need to capture, which fields represent or describe those classes, and the verbs are going to give you clues on the relationship between those classes, between those concepts. Oftentimes you'll analyze nouns next to each other, right? And when you might have instead analyzed 3 nouns or 4 nouns together in a verb phrase, right? And depending on how you interpret it, you might come with a different conclusions of what the class diagram might be, right? So instead of having 2 classes being related, there might have been 3 classes that are related to one another, or 4 that are related to several verbs. So that typically will give you either redundant or inadequate relationships, right? On how you oversimplified your interpretation of the facts. So you'll have to come back a little later and perhaps reread your specifications and realize that, hey, I oversimplified. And that will give you, inevitably will give you some inadequate relationships or redundant relationships. You'll try and, for every loop that you might identify, any cycles in your class diagrams, you might want to make sure you don't have any redundancies. Do I really need this additional association? If I follow this particular path from one class, can I reach this other class, or can I reach it from some other class, right? If you have 2 different paths, that's a clue that you might have a redundancy, right? And remember, redundancy breeds inconsistency. We want to remove those things. You'll go back and forth trying to identify whether a field should be a concept should be an attribute or a field of some class, or whether it should be a class on its own, right? Like a faculty, is it enough to capture an attribute, or should we have a whole class for it, right? Is a faculty important enough to have its own class? Typically, you'll iterate over this several times, right? Removing redundancies, removing some inadequates, reifying some mapping tables and whatnot. And this is this is what we're asking you in the assignment, in the first assignment, to do, right? To go through this, through the specifications, come up with an initial first approximation of what the class diagram might be. Okay, it should be very naive. You shouldn't think about it too much, right? The first approximation is intended to be wrong, all right? And the assignment asks you to iteratively give several versions of the class diagram as you identify inadequacies or you reason about your class diagram, right? And to think out loud and explain, right, in paragraphs, explain your thinking. Okay, so I think this association is not necessary because I can already go follow a particular path. I'm going to remove it, right? And I want you to show us a before and after of various class diagrams as you think about them. Yes? So you might have an initial first approximation, right? And then small snippets as you make decisions over certain iterations of the same class diagram. Make sense? So that's going to be your first assignment, right? Go through this algorithm of designing a good class diagram. Anyway, so requirements, yeah. So requirements, as I mentioned earlier, are the results of having interviewed your clients over a number of periods, a prolonged amount of time, or in an agile sense, meeting with them regularly to receive feedback as from where you're going. So here's an example on describing the university theme that we're going to be using throughout the semester of describing academic departments like mathematics and drama, offering different courses. You might have non-academic departments. This one is intentionally inserting information that is irrelevant to the problem, and that's very common. That you're reading through the specification, there'll be lots and lots of irrelevant facts that are not going to be represented in the data in the final data representation, and that often is, through you having conversations with the user, with the client, on whether things are relevant or not. Now, that's one thing that you might not have going through your assignment. You won't have the benefit of having a client and asking those questions. Yes. So we'll do our best to answer questions on Piazza. We might often give you, conflicting answers, or we'll be vague on some of these, and that'll be fine. We just want to see your thoughts on how you dealt with these inconsistencies, right? How you dealt with some vague things. Certain things are not going to be described, right? So you make some best guesses. Right, that for instance, a person, we might not even mention that a person has a first name, a last name, right, or date of birth, okay, because those are just common things. They're common knowledge. So you'll make first approximations on certain fields that you think should be there, but were never mentioned. Yes, it's very, very common. So we'll describing students. Their graduation year, their major. So this is describing our university. Campuses and cars and permits and license plates. Some business rules or different things that the client has requirements that they want to be able to answer or query the database. Typically these will be from perhaps having interviewed the folks who do data entry or printing reports. Or following them around and see what they do from day to day. What forms are they filling out? What complaints do the clients have? So from having interviewed lots and lots of folks, you come up with this, some formal capture of those requirements. Right? What are the pain points of the current application? And so a first approximation is as part of the process of coming up with the class diagram, you might come up with a first list, a dictionary of all the verbs, all the nouns, also capturing maybe a verb phrase from where the nouns were identified. Some of these verb phrases will be noun, verb, noun. Some of these verb phrases will be noun, verb again, and another noun. Okay, where it's associating not two nouns, but it's associating three nouns or four nouns. Okay, that's part of your analysis. How many nouns are associated here? 2, 3, 4. How many? Excuse me. Some of the part of this is determining what the scope of the database is, and the granularity of your database. Yeah, for instance, in a university database, if you're capturing the database for a particular university, typically, the concept of university itself won't be captured in the database. Okay. For instance, imagine you were doing a database for a university and you have a table called university. Presumably you would have records inserted in the table university, but you're really modeling a single university. Yes. So what would you put in this table? A single record for your university. Make sense? Right, so it makes no sense to even have a university table, right? Because really the information, all the information is about that one university. Yes, so it's important to identify what the scope of the application is. Right? If you were instead the Department of Education, where you're keeping track of lots and lots of universities, then it makes sense that you do have a table of universities where you have many, many records for each one of the universities, yes? But if you are one of those universities, it makes no sense to have a table called university. Make sense? So it depends what it is that you're capturing. Also, the granularity, again, the example I gave earlier about how much do you want to model about certain things, about a car. Well, if you're for a motor company, then yes, you have lots and lots of tables about a car. But if you're a university, probably you just have a field. Okay, so again, it depends on the granularity. So here's a preliminary class diagram where you have students, departments, grade, professor, and you have some of these relationships. And again, your domain knowledge, your experience about a particular domain might inform this, right, on how is it that you might get started at, right? So lots of you are going to have different solutions. There won't be one single right answer, okay, from your assignment. But certainly there's certain aspects, some principles, right, that we certainly want to capture. If you're completely ignorant of a domain, you won't be able to tell one noun from another noun, right? You know, if you're completely ignorant about a domain, you don't even know what the nouns mean, right? You might know that it's a noun, okay, and that's about it, okay? And so you might not know that certain nouns are describing other nouns, or that certain nouns make up other nouns, right? So you might come up with a very, very naive class diagram where every single noun is a class, right? Every single noun is a class, right? So every noun is represented here with a rectangle box, right? As you go through the iterations of understanding that certain nouns are actually a part of some bigger whole, right? Then you might say, oh, well, actually, no. Some of these nouns are actually fields in some other class, right? And so this will be different iterations of merging some of these classes, or some of them, maybe the year might be part of the section, or the year might be part of the student, but not a class on its own. Okay, so those decisions come along as you analyze a particular domain. All right, so first let's look at some of the inadequate relationships. Okay, so what do we mean by inadequate relationships? So it might be that as you were reading this, okay, and you were considering, one noun related to another noun, you might draw this in a diagram. For instance, you might have read that students can enroll in a course. So you draw that. You draw them and you say, okay, well, I'll draw a student and then the association that enrolls in a course, right? And you draw that. And then later on in another sentence down further, you read that a course has many sections. Yes? Right? And so you draw that. And you say, well, here's a course, has many sections. Okay? Now, as you analyze a little further, you might say, wait a minute. If I read the whole sentence or the whole paragraph, you realize that a student doesn't actually enroll in a course. They actually enroll in a section that is associated to a course, right? Okay, so the misinterpretation of the way you read the sentence might either give you this class diagram, or it might be that you realize that this one is missing a relationship between the student and the section. Nowhere here am I capturing that a student is enrolled in a particular section, right? This class diagram does not answer that, right? What student is enrolled in what section? So you might have to bring that actually down here, right, and have a three-way relationship between students, sections, and courses. Or that it might, or the section might fit in between these two, where you have a section referencing a many-to-many of students and sections, and then a one-to-many relationship between a section and a course. So depending on how you read it, you come up with this or another one. Yes? So that's what we mean by an inadequate relationship. Okay, where you might first come up with this, but then you realize that that section actually should be in between students and courses. Yes? Right, because it doesn't allow you to capture the relationship between student and section. Right. So you should based on the queries and the description, you have to consider every path, right, in the class diagram, and see if those paths allow you to answer or navigate the data structure as you have the description. So here's a couple more. Here's we have receives. This receives over here, right? Notice that it has student receives grade. That was a literal sentence in the specification, right? And in a later sentence, there was the grade. The professor assigns grades, right? There was also a particular sentence in the specification. There was another one that says, these two, receives and assigns. Yes, right. But if we go back to the original sentence or the paragraph, we realize that it didn't say student receives grades. Okay. It actually said something like student receives grades for an enrolled section, right? So this is actually not a binary relationship between students and grades. It's actually a three-way relationship between student, grades, and section, right? So you need to look at the verb phrase and see which ones are related to one another: students, sections, and grades. And same thing with the professor. We read it as a binary relationship when we said professor assigns grade, when we should have really read professor assigns grades to a student, right, in a particular section. So it could be a three-way relationship, or a two-way relationship, or a four-way relationship, depending on how we read it. So this first approximation of student receives grades actually should have been a three-way relationship, right, where you have a student, a section, and a grade. Right? So this is a three-way relationship instead of a two-way relationship, where if you give me a particular student, if you have a particular instance of a student, well, that student might be in multiple sections. Right? It could be in multiple sections, and in a particular section, they'll have one grade. Right? So if you give me a combination of a particular student in a particular section, there'll be only one grade for that particular student. Okay? Or if you have a particular grade, A, B, or C, or whatever, many students in many sections will have the same grade. That makes sense, right? Any combination. So, or if you have a section, right? You're going to have many students that have the same grade. So that's how you read it. So anyway, we mentioned earlier that this would be just fine in UML, right? To capture something like this. But if you're actually going to implement it in a relational schema, there's no way to implement this. Right? So the only way to implement this is to replace it with a new class, right? That implements the relationships explicitly. Right? That says that the grade assignment has references to all the participants. Right? It has references to what student enrolled in what section got what grade. Okay, this is somewhat what you would do in the language of using or interpreting a verb as if it were a noun, right? Or converting a verb into a noun. So, for instance, receives might be changed. So the verb receives might be changed to a noun representation as a grade assignment, right? As a noun, as an adjective. Okay. So going from this conceptual representation to this more concrete representation, we also often refer to as a reification. We have reified diagram, made it more concrete, something that can actually be implemented in a lower level representation. Okay. So anyway, so this is. I mean, you might see where we're going. This eventually, this is going to become our enrollment table. Right. Our enrollment table is the one that has foreign keys to what student was enrolled in what section, right? And eventually, what we're going to do is that we're going to subsume this grade and we're going to bring it into the enrollment table, right? That's where we're going. So yeah, reification, as I mentioned earlier, is the act of making more concrete for implementation. So what do we do here? We replaced grade, professor, section, student where we replace it with this noun, right, in between that relates the section, the student, and the grade, right? So we have this new relationship. So we can look at some other relationships that might be redundant, okay? That might be already captured by some other association, right? So for instance, we have in our class diagram, we have the relationship that the grade assignment is assigned by a professor. Okay. Now this would if the rule says that in a particular section only one professor can possibly teach that section, it's already understood that if you know the section, you know the professor who's teaching it, right? And only that professor can possibly assign the grade. Right? So it would be this additional information here that for the assignment was assigned by the professor, right? I can also know the same exact information by knowing the section. If I know the section, I know the professor. There's only one professor in that section, and he's the only possible person who can assign it. Yes? Okay. So this relationship is redundant. I already know who the professor is and who assigned it. I don't need this. If I leave it there, right, I can answer the question, who assigned it? I can either go this way, or because I know that a section only has one professor, I can navigate to the section and then navigate to the professor. So there's two ways that I can answer that question. Who assigned it? Yes? So if you can answer the question in two different ways, it's redundant. Right? And redundancy, as I mentioned earlier, breeds inconsistency. Now, what if this foreign key points to this professor, and this foreign key, by definition, would have to point to the same professor? Yes? Ideally, that would be the case if I keep this association. Yes? But what if, for some reason, an error in my coding, right? I have this foreign key pointing to one professor, but this foreign key somehow pointing to some other professor. Right? That would have never happened if the association wasn't there in the first place. Yes? So that's why we try to remove these redundancies. And for as good a programmer as you might be, okay, you might cause this mistake, right? That these foreign keys are somehow not pointing to the same person. So to eliminate the possibility of that even happening, right, we remove any redundancy. Make sense? Okay. So we remove that. Now, not all cycles, because this is a cycle. Whenever there's a cycle, there's a question of saying, wait a minute, I can navigate this way, but I can also navigate this other way. Right? Whenever there's a cycle, there's a question: is it redundant? Right? And you should ask yourself. Right? Every cycle, every path should be considered. Okay. But always with the question in mind. In this one, the question was, can I answer who assigned the grade? That was a query. Can I know who the professor is that assigned the grade? Yes. With that question, that assigns is redundant. Right? If I have a different question, then that assigns is not redundant. So it depends on the question. Right? Here, in this one, the question might be, can I know which students are enrolled in what department? Okay, well, I can certainly navigate from students to department, or from department from students, right? And I can tell you, I can answer that question. So since I have a cycle here, I might also ask myself, well, can I also answer the same question if I navigate following this other path? Starting from the student, going to a grade assignment, to the sections, all the way to. But as we navigate through this, we'll notice that we have a many-to-many here, right? Since we have a many-to-many, if you start from the student, when you get down to the department, you can't answer exactly which student is in what department, because it was lost in this jump, in this many-to-many jump over here. Right? You can't follow along of knowing exactly which student is enrolled in which department. So you can't answer the question of which student is enrolled in what department if you follow this path. Okay? So based on that question of whether, can you answer which student is enrolled in which department, for that question, these two paths are not redundant. Okay, one is not redundant with the other, right? So in these cases, both could stay. Actually, if I remove the majors in, I no longer can answer which student is enrolled in which department. So I need to keep it. Right, I need to keep it. So both would stay. So not all cycles are redundancy. Right? You need to ask the question of query, and then you can answer whether it's redundant or not. So anyway, so always check all the relationships in redundancy, following all the paths. So here we remove some of these redundancies. So we remove the assigns. So we don't have the assigns here anymore. The enrolls in was also redundant, right? The enrolls we remove because we can follow along with the grade assignments. Is the enrollment there? So yeah, so so this is the kind of thinking that we want to see in the assignment, in your first assignment. Okay, show us multiple versions of the class diagram as you think about it, right? And your thought pattern. Again, there's not going to be a one right answer, right? We just want to see your thought patterns, and if you can defend your decisions, you're good. All right, so week to week, where you might have a case where you have a student in a department. So in our description, in our specification, a student could possibly be enrolled in one single department. You can only be in one department. But what if the specification might have said that we would allow you to be enrolled in multiple departments? You have a major, you have a minor, a double major, whatnot. So it would look something like this, right? You have a many-to-many. Again, in UML, that might be fine, right? But typically, if you're going to implement this in a relational database, you would replace it, you would reify it, right? And creating a mapping table that would have foreign keys pointing to both records. All right, so now that we have this many-to-many, let's look at some of the challenges we might have if we have this data model. So for instance, if now that you can be enrolled in multiple departments, before you might have had just a single GPA, right? Because you only have one department or one school. You belong to one school, you have one GPA. But now that if you belong to many departments or multiple schools, you might have a GPA that is associated with each one of the majors, right? You might have an overall GPA, and you might have a GPA for each one of the departments. Where do you keep that? Okay, so it looks like the GPA. If when you were associated to a single department, it might make sense that the GPA was associated to the student, because there's only one student, one department. There's only one GPA. So it's fine for the student to just have a reference to its GPA. Make sense? Right? But now that you can have multiple GPAs, you might be tempted to also associate it to the student. Right? Because the GPA was associated to a student. Now the major GPA can also be associated to a student. But the problem with this is that this doesn't answer the question, which GPA belongs to what department. Okay? This one over here, all by itself, just tells me that the student has a GPA, but I can't tell you for which major. I can't tell you for which one. So this tells me that this is wrong. This is an inadequate relationship, right? It's in the wrong place, right? We need to move it around and say, no, this GPA actually is a three-way relationship between the department, student, and the GPA. So it's a three-way relationship. We reify it, and we substitute it with a concrete class that associates all three, right? That has references to all three. Okay. But what if that department or the university allows you to maybe be a what is it? Where you can join the university, but without declaring which school you're going into or which department that you're going into. So you have like a year or maybe 6 months to decide which department you're going to go in. Right, undeclared. That's what it is. You're an undeclared student. So the relationship between the student and the foreign key to the department might actually not be there. Meaning, I don't even have a foreign key pointing to any department. Yes, right. So this is an optional relationship. Right, I might be enrolled, I might not be enrolled in any department. In that case, how do you capture the major? It might make no sense to have a major entry point if I'm not enrolled in any department, right? So how do you model that kind of relationship, right? It might make no sense to have a relationship or an entry point if it's not there. So the way to capture it might be to have, again, understand that it's a three-way relationship, okay? And the way to capture the optional relationship between a student, and if they are enrolled, right, you have a one and an optional entry point in here. So meaning there's only going to be an entry into this table or into this class, into this instance, only if you're actually enrolled in the department, and then you would have a GPA along with it, right? If the student is not even enrolled in any department, there is no record here, right, that references any department or references any GPA, right? It says a 0 to 1 optional in there, okay? All right, so there might be some optional ones in here, like the permit. The permit is also optional. Whether the student brings a car or not brings a car, depending if they get a permit or not. So it would be we would use the same idea, right? We would create a multiple several nouns associated together in a three-way relationship, and whether they have a permit or not, we would capture the additional information. For instance, in this case, it would be that if you're a student, you might have an expiration date associated. But if you're not a student and you're a faculty, you might not. You won't have an expiration date. So depending on who you are, you would have that information or not. So reify week to week. Strong, one-to-one. So in 1-1, if this were a one-to-one relationship, oftentimes the question might be, whether we even should have a class outside of it, or perhaps we might want to merge the content of that particular record into its parent. Like, for instance, the way we split track and lyrics, right? You might have challenged that and said, well, why don't you just have lyrics as part of the tracks? Why does it even have to be a separate table, right? And that's a valid challenge. So why split it in the first place? Now, typically we typically do split it so that we can distinguish two different concepts. Permit is not necessarily something that is associated to all students, right? So it might be it might be a decision, a stylistic decision on whether to merge it or not merge it. But if you merged it, you would have something like this. You have the student, which has maybe the permit information, but now it would have to capture also foreign keys and primary keys that would link to the other concepts or the other classes that the permit was referencing to. Right, so all the primary keys and foreign keys that used to belong to the permit are now subsumed by the student class. Adding attributes to classes. Yeah, right. So there might be other nouns that were not specifically mentioned in the specification, like saying that persons have first name, persons have last names, persons have date of birth. Those are all implied, and oftentimes are not even mentioned in the specification. Also, some determining, what's the granularity that you want to capture or model something. For instance, in our car, we're just deciding that a license plate is plenty, right, to capture the model of a car. Also, some decisions were made here that certain classes were not even worth capturing, like a faculty. Right. Instead, it decided that an attribute was enough. Right. The professor username was enough to model the professor. Again, that was a design decision. Or that some things that we decided that were classes, we might decide that it's not worth keeping track of that. Right. That it should be maybe just an attribute in a larger class. So, for instance, the class year, or the class grade, probably that's not even worth having a whole table for it or a whole class for it. So we might decide to merge them into 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 the classes that are referencing it, right? So for instance, if you have year both for student and section, we can then represent that year as a field of section and another field of student, right? And same thing here for grade. We might decide that it's not worth having a whole table or a whole class for that, so we might merge it into the enrollment. Yes. So having done all those manipulations, we actually end up with the class diagram we were intending to end up at the end, right, where we started at the beginning, students, department, course. So just to prove that we had already chosen a very good class diagram, very well designed. Okay. All right, so let's stop here because I want to